Good morning, all of you. My name is Sai Kiran. I'm your chemistry lecturer. If you remember, in our last class, we discussed shapes of subatomic orbitals and nodes and important graphs related to psi versus r and psi square versus r. These two topics are very important topics. Frequently, questions are asked from these two topics. One is how to calculate nodes, angular nodes and radial nodes. And second one is how to draw the graphs related to psi versus r and psi square versus r. If you don't watch that video, please go to my channel and watch that video, then come back to this video. Today we shall be discussing about electronic configuration. It is nothing but distribution of electrons into orbitals of an atom is called electronic configuration. It is represented as 2px2. Here 2 represents shell and this P represents subshell and this Px represents orbital and this 2 represents number of electrons. In order to write the electronic configuration, we must follow the 3 rules. Let's see one by one in detail. The first one is Above principle. According to this principle, electrons are filled into the orbitals of an atom in order of their increasing energies, and that atom must be present in ground state. And less energy orbitals are filled first with electrons, then higher energies. In case of single electronic species, the energy increasing order is only depend on the principal quantum number, that is n values. Let's see. 1s less than 2s, next 2p. Here n value is same, so energy is also same. Less than 3s, similarly equals to 3p equals to 3d. Less than 4s, 4p, and so on. 4d equals to 4f, like that. This is the energy increasing order of orbitals in single electronic species. This is not applicable for multi-electronic species. For that, we have one rule, that is n plus L rule. Or Bode-Varis rule. This rule depends on principal quantum number value and azimuthal quantum number value, that is n value and L values. As per this rule, whose n plus L value is less, that having lesser energy, and whose n plus L value is more, that having more energy. N plus L value is less, that having lesser energy. N plus L value is more, that having more energy. And if n plus L value is same, we getting 2 orbitals, n plus L value is same, then follow the based on n value, principal quantum number. If n value is more, energy is more. N value is less, energy is less. Let's see how to calculate this n plus L value for orbitals. Minus 2s, 3s, 3p, 3d, 4f, 4f. N plus L values equals to, in the first case, here we know that L values for the orbitals. For s orbital equals to 0, p orbital is equals to 1, d orbital is equals to 2, f orbital is equals to 3. These are the L values. Here n value is 1 plus s value for s orbital is 0. Sum is 1. Here n value is 2 plus s orbital is 0. Sum is 2. Here 2 plus L value for p orbital 1. Sum is 3. Here 3 plus 0, 3. 3 plus 1, 4. Here n value is 3 plus L value for D is 2. It comes out to be 5. Here n value is 4 plus S value is 0. Comes out to be 4. Here 4 plus 1, 5. Here 4 plus 2, 6. Here n value is 4 plus L value for F orbital is 3. That equals to 7. These are the n plus L values for these orbitals. Now arrange them in their increasing order. Let's see. Least energy is here. So first least orbital is 1s. Less than, next least energy is 2s. Less than, here we get same n plus L value. In this case, we follow the who's having lesser n value, that is having less energy. These two cases, here having less energy, less n value. So here having less energy. 2p comes here, less than 3s. Here also same n plus L values. In these two, this having lesser n value. So this comes first. 3p. Then 4. Less energy is there. 4s. After that 5. 3d. Then 4p. Then 4d. Then 4f. This is the energy increasing order of orbitals according to n plus L rule. Let's see the diagrammatic representation of these orbitals. First, electrons field in least energy, that is 1s. Then comes to field 2s. Then comes to field 2p. Then 3s. Then come to this side 3p and 4s. Then come to this side 3d, 4p, 5s. Then come to this side 4d, 5p, 6s. Then come to the 4f, 5d, 6p, 7s. This is the diagrammatic representation of orbitals according their increasing energies. Now come to the second rule, that is Pauli's exclusion principle. This rule states that no two electrons can have same set of 4 quantum numbers. We have 4 quantum numbers. They are n, principal quantum number, azimuthal quantum number, magnetic quantum number, spin quantum number. No two electrons can have same values of 4 quantum numbers. Let's see with example. For example, 2s orbital. In this 2 electrons, 2s2. For this electron, n value is equals to 2. This L value for s is 0. M value is equals to 0. S value is plus half. For this electron, n value is 2. L value is 0. M value is 0. Because M value depends on L value. S value is minus 1 by 2. In this case, N value, L and M values are same values, but S value is different. This is the Pauli's exclusion principle. Let's see one more example. 2p2. For this electron, N value is 2, L value is 1, M value is minus 1, S value is plus 1 by 2. For this electron, N value is 2, L value is 1, M value is equals to 0. We know that M values for this minus 1, 0, plus 1. S value is minus plus 1 by 2. Here, N, L and S values, we got same values, but M value is different. No two electrons can have same set of 4 quantum numbers. Now, we will try to add another way of electrons. That is, for example, in this electron, I am filling with same spin, like this. For this, we get N value is equals to 2, L value is equals to 0, M value is equals to 0, S value is plus half. N value for this, N value 2, L value 0, M value 0, S value comes out to be plus half. In this case, we got same values for all quantum numbers. This is the violation of Pauli's exclusion principle. This is incorrect. Let's see one more way. Now, I want to add one more electron to the same orbital, like this. In this case also, we get same values for this and this, N, L, M, S. This is also violation of Pauli's exclusion principle. From these two examples, we get one more important point. An orbital can accommodate maximum of 2 electrons with opposite spin. That is the Pauli's exclusion principle. The maximum number of orbitals present in a shell is equals to n square. For example, in the first shell, number of orbitals is equals to 1 square, that is 1. In case of second shell, number of orbitals is equals to 2 square, that is 4. Similarly, the number of electrons present in a shell is equals to 2n square. In this first case, 2 into 1 square, 2 electrons. In the second case, 2 into 4, 8 electrons is present in the second shell. Now come to the third rule, Hund's rule of maximum multiplicity. This rule deals with the filling of electrons in degenerate orbitals. Now, what is this degenerate orbitals? It is nothing but these orbitals having equal energy. For example, p orbital. In these three orbitals, px, py, pz. These three orbitals having equal energy. So, these are called degenerate orbitals. In other words, with the orbitals having same n and l values. For example, these orbitals n value is 2 and l value is 1 for these three orbitals. So, same n and l values are, these three orbitals are called degenerate orbitals. According to this rule, electrons are filled into the orbitals of a subshell in such a way that which is having maximum multiplicity will having more stable. Let's understand. For example, we have two ways to fill electrons. These three electrons. For example, here 2, here 1. Similarly, here 1, 1, 1. Now, we want to calculate the multiplicity. For this, formula is equals to, multiplicity is equals to 2s plus 1. Here, s is the sum of spin or total spin. Now, we calculate the s value for these orbitals. For this, plus half. For this, minus half. For this, plus half. Here, plus half, minus half gets cancelled. Total sum is equals to plus 1 by 2. Here, for this electron, plus half. For this, plus half. For this, plus half. Here we get total sum is equals to 3 by 2. Now, calculate the multiplicity. That equals to 2 into s value. 1 by 2 plus 1. Here 2 gets cancelled. Multiplicity total value comes out to be 2. Here multiplicity is equals to 2 into 3 by 2 plus 1. Here 2 gets cancelled. Total value comes out to be 4. More the multiplicity value, more will be the stable. So this is the stable electronic configuration. We follow this way. This is the incorrect way. Based on this example, we get one more important point. That is, after filling one electron in each orbital with same spin, then only pairing will take place. These are the three rules for writing the electronic configuration. Let's see how to write the electronic configuration. According to Aufbau principle, energy increasing order of orbitals is 1s, 2s, 2p, 3s, 3p, 4s, 3d. S sub shall have only one orbital. P sub shall have 3 orbitals. D subshell having 5 orbitals. Now let's see the electronic configuration, how to write the electronic configuration for elements. First one is hydrogen. Atomic number is 1. It has only one electron. These electrons are filled in the least energy of 1s. Electronic configuration is 1s1. Next, helium. Atomic number is 2. It has 2 electrons. 2 electrons are filled like this. Electronic configuration is 1s2. Lithium. It has 3 electrons. Next electron filled in this orbital. Electronic configuration is 1s2, 2s1. Next, beryllium. It has got 4 electrons. Fourth electron is filled in this orbital. Electronic configuration is 1s2, 2s2. Next, boron. It has got 5 electrons. Next electron is filled in p orbital because each orbital accommodates maximum 2 electrons according to Pauli's exclusion principle. Electronic configuration is 1s2, 2s2, 2p, 1. Next one is carbon. It has got 6 electrons. Electronic configuration, 6 electron is entered into the next shell. According to Hund's rule, after filling one electron into each orbital, each degenerate orbital, then only pairing will take place. This filling is with same spin. Electronic configuration is 1s2, 2s2, 2p, 2. Nitrogen. Atomic number, electronic configuration is 1s2, 2s2. Next electron filled here. 2p, 3. Of oxygen, atomic number is 8. Electrons are 8 electrons. Next electrons are filling here. Now pairing will start. 1s2, 2s2, 2p, 4. Fluorine, atomic number is 9. Number of electrons is 9 electrons. Next electrons are filled in this orbital. Electronic configuration is 1s2, 2s2, 2p, 5. Next, neon. Atomic number is 10. 10 electrons are present. Next electron are filled in this orbital. Electronic configuration is 1s2, 2s2, 2p, 6. This is the noble gas. Instead of this electronic configuration, we can directly write this symbol. Let's see. Sodium. Atomic number is 11. It has got 11 electrons. Electronic configuration is up to 10 electrons neon. Then 1 electron enter into the 3s1. Instead of this electronic configuration, we can directly write the noble gas. Next, magnesium. It has got 12 electrons. Next electron enter into the s orbital. That is neon, 3s2. Next, aluminium. Atomic number 13. Electronic configuration, electrons are 13. Electronic configuration is next electron enter into 3p orbital. Neon, 3s2, 3p1. Next, silicon. It has got 14 electrons. The electronic configuration is neon, 3s2, 3p2. Next, phosphorus. It has got 15 electrons. Electronic configuration is neon, 3s2. Next electron enter here, 3p3. This is the way of writing electronic configuration. Let's see the exceptional cases of electronic configuration. That is, exceptional electronic configuration of chromium and copper. The expected electronic configuration of chromium is chromium, atomic number 24. Argon, this is noble gas, atomic number 18. 3d4, 4s2. This is the expected electronic configuration of chromium. But actual electronic configuration of chromium is equals to argon 3d5 4s1. Similarly, expected electronic configuration of copper atomic number 29 equals to argon 3d9 4s2. But actual electronic configuration of copper is argon 3d10 4s1. In this case, 5 electrons means this d subshell is half filled. In this case, 10 electrons. Because of this, actual electronic configurations are unexpected electronic configurations due to the half-filled and fully filled orbitals. Half-filled and fully filled orbitals are more stable than partially filled orbitals. In this case, this 3d and 4s orbitals are energy is nearly equal. So they are become degenerate. So electron shifting takes place. Further, it's getting half-filled electronic configuration, it's getting fully filled electronic configuration for getting more stability. Let's see the stability order. In the exceptional electronic configurations, the actual electronic configuration of chromium and copper are considered as a ground state electronic configurations. That is not an excited state electronic configuration. We can write directly the actual electronic configurations of chromium and copper when they are asked in the questions. Now come to the stability order. Fully filled is more stable than half filled. Half filled is more stable than partially filled. Now the question is, how we know this fully filled is more stable than half filled is more stable than partially filled? For that, we have two reasons. First reason is symmetrical distribution. Let's understand with one example. D4 orbital, D5 orbital. In this, 4 electrons is present. In this, 5 electrons are present. In both the cases, we have symmetrical distribution of electrons. But when compared to D4 orbitals with D5 orbitals, it has more symmetrical distribution of electrons. More symmetrical distribution means more stability. So D5 is more stable than D4. And second reason is exchange energy. When electrons with the same spin, which has capability to exchange their positions, when they are present in degenerate orbitals of a particular subshell. Let's understand. This electron have three possibilities to exchange their position. So 3 plus this electron have 2 possibilities to exchange their position. 2 plus this have only one possibility, 1. Total exchanges are 6. Every exchange, they release some energy. That energy is called exchange energy. In this case, this electron have 4 possibilities to exchange their position. And this electron have 3 possibilities. This electron have 2 possibilities. This electron have only one possibility. 4 plus 3 plus 2 plus 1. Here total exchanges are 10. When exchanges is more, energy release is more. When energy release is more, stability is more. Because atom loses more energy, it has less energy, then it gets more stability. Now come to one of the small and important topic, that is magnetic movement. It is indicated with mu. Formula for this is mu is equals to n into n plus 2. Units are Bohr magnetons. This gives the information about that atom or ion, it has paramagnetic nature or diamagnetic nature. For example, if mu is not equals to 0, it indicates the paramagnetic nature. If mu is equals to 0, it indicates the diamagnetic nature. Let's see one example. For example, manganese dipositive. The outermost electronic configuration is 3d5, 4s0. Here 1, 2, 3, 4, 5. This n represents number of unpaired electrons or single electrons. In this, we have 5 unpaired electrons. So n is equals to 5. Now mu is equals to root of 5 into 5 plus 2. That equals to 5 into 7. That equals to 35 Bohr magnetons. If mu value is more, that means unpaired electrons is more, paramagnetic nature is more. That's it, today class. With this class, the chapter atomic structure is completed. And I will make one more video on this chapter. In that, we will discuss all important formulas with tricks with previous year questions.